It is a pleasure to welcome you to the third edition of the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP lecture series is a pro bono initiative led by Dr. Partha Mishra and Professor Sarat Das. Initiated in 2020, it is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. The International Workshop on Biogeotechnics was hosted in 2022 during the third edition of the AGERP lecture series. The following lecture on sustainable geotechnical engineering with biopolymer-based soil treatment, from research to practice, was delivered by Professor Ilhan Chang at this workshop. Dr. Ilhan Chang is an Associate Professor with the Department of Civil Systems Engineering at Ajou University, Republic of Korea. Dr. Chang earned his Bachelor of Science in year 2000, Master of Engineering in year 2004, and Doctor of Philosophy degree in year 2010 in Civil and Geotechnical Engineering from Korea Advanced Institute of Science and Technology KAIST. Main topics of his MS and PhD dissertations were soft soil evaluation using elastic waves and soil stabilization using microbial biopolymers, respectively. Prior to his current appointment, Dr. Chang gained professional careers as a research assistant professor at KAIST from 2010 to 2011, senior researcher at the Korea Institute of Civil Engineering and Building Technology, lecturer and senior lecturer at the University of New South Wales, UNSW, Australia. Dr. Chang and his research group, SURE3 Geotechnical Engineering Research Group, are mainly focusing on multidisciplinary research for emerging geotechnical engineering subjects such as soil characterization, ground improvement, soil erosion and preservation, biopolymer-based soil treatment, biological and bio-inspired soil treatment, anti-desertification, hydrogeotechnical engineering, new civil engineering materials, and sustainable urban development.
Okay, as already been introduced, I'm Ilhan Chang. As already been introduced today, I'm just going to share my current and past developments and research outcomes related to sustainable geotechnical engineering. Especially, we were focusing on biopolymer-based soil treatment, which the acronym becomes BPST. So I'm going to show some research scale findings from the laboratory and how we are attempting to utilize these techniques to practical implementations. So today, my lecture will follow these orders. So I'm going to talk about what is my dream for sustainable geotechnical engineering is, and how BPST can contribute and how it works to enhance or improve some properties of soils, and what is our goal, future goal, to implement this BPST technology for actual sustainable engineering practices. So, well, I'm currently working at Ajou University in South Korea. Prior to my current occupation, I worked with the University of New South Wales in Australia as an academic lecturer and senior lecturer for up to 4 years. Before UNSW, I gained my professional research careers as a senior researcher at a national research institute in South Korea. So, well, let's start with the concept of sustainable geotechnical engineering. So, as you already realize, threats such as extreme temperature rising, glacier melting and sea level rise, heavy rain and floods, well, soil erosion, land degradation, and also following desertification are becoming more common as a result of the current climate change. So, well, for instance, just in last year, in 2021, Europe, in Italy, there was the highest temperature ever recorded in what? In the human history. So, what does this mean? The Earth is getting hotter and hotter, and that climate increase is resulting more severe and more frequent geotechnical engineering hazards events. So what happens all around the world? We have more concentrated and heavy downpour. They are inducing what they're rendering floods. And sometimes these floods can also accompany severe failure, subsequent levee or earth dam failures due to these abnormal climate events. So just 3 years ago, we had a very severe dam collapse in Laos and a very heavy flood in Japan, which also caused serious and significant casualties and costs. Furthermore, as a result of global warming, more intense wildfires are happening all around the world. So resulting in the increased land degradation and geotechnical engineering risks such as landslides. And as a lump sum, we are facing more and more and severe economic damages and costs related to these climate change related geotechnical engineering hazards. And for a particular subject, if we take a look on desertification, my research group, we have performed a deep data analysis 6 years ago to see what is actually desertification related to in terms of geotechnical engineering. So when we just randomly selected 105 soil samples data all around the world, and we just analyze their particle distribution. And we found that in terms of geotechnical or soil science, desertification can be explained as a soil composition transform from a well-distributed soil to a poorly graded soil with the reduction in the clay content and relatively the increase of sand content. So it means that desertification can be expressed as a soil composition transform from a cohesive soil to a cohesionless soil. So what does this cohesionless soil mean? Because they lose interparticle interaction and cohesion, they become more prone to wind or water-induced erosion events. And so nowadays, all governments and institutions are aiming to reduce to combat to this current climate change. So the European Commission seeks to reduce the greenhouse gas emissions by more than 65%, whereas the US government wants to reduce the emissions by 50% just in 10 years. So what does it mean? We have to do something urgently to reduce CO2 emission. In geotechnical engineering, actually, we are facing a dilemma. We generally execute ground improvement procedures and practices with conventional cement to enhance and improve the soil strength. However, cement has been commended as a significant CO2 emitting material, accounting for over 8% of worldwide CO2 emissions. So as a result, what we have to do, we need to find a new geotechnical engineering material and method to to reduce the usage of this high CO2 emitting material in our construction and geotechnical engineering field. So as an alternative, I was focusing on biopolymer-based soil treatment. So the basic idea is like this. Well, despite the fact that modern soil mechanics regards the ground and soil to be an inorganic material, a range of organic compounds are produced in natural soil by small organisms and bacteria. And what are these organic compounds, and what is the role of these compounds? They have some very distinctive functions to the soil. So, specifically, the chemical activities of microorganisms precipitate inorganic minerals such as calcite, or sometimes organic compounds such as biopolymers. The mechanical properties of the soil are affected by these excretions. Particularly interparticle bonding can be improved, or sometimes these precipitations or these excretions can clog and fill the pore sizes and induce a conductivity reduction or conductivity control or something else. So among other different types of biological soil treatment approaches, microbiopolymers are high molecular polymers produced by living organisms, which have been widely used in a variety of industrial fields, except for civil and geotechnical engineering. And biopolymers can be classified into three main categories. So the high molecular chain type polysaccharides, gelatin polysaccharides, and protein and lipid. Because each group has its unique set of advantages and disadvantages, careful selection is essential in geotechnical engineering. So today I'm going to show what are the expectations and what are the current limitations of using these biopolymers for soil treatment and ground improvement. Well, unlike MICP or EICP, while endocultivation is essential for microbial-induced calcite precipitation, MICP, for biopolymer treatment, exocultivated biopolymers can be just produced out from the soil from a well-controlled facility. We just separate the produced biopolymers and we just utilize them as what? As soil binders. So we can mix it with soil, we can inject them into the soil, well, just like other pre-existing common soil binding types. So this is one of the biggest advantage of using biopolymers for soil improvements. Because what? We can also control the quantity. For MICP or EICP, actually we cannot control how much of calcite will be produced for a certain time. We cannot ensure it. But for biopolymers, okay, we can just set, okay, we want to mix 0.5% or 1% of biopolymers to the mass or the weight of soil, then we can just conduct it. That is the most biggest advantage of using these biopolymers. So first of all, let's see how these biopolymers interact with soil particles. Actually, biopolymers are they are hydrophilic. They have a high hydrophilicity. So with the presence of water, they are well dissolved into water and they form a viscose hydrogels. So these hydrogels actually have a shear thinning and thixotropy characteristics. With a small amount of biopolymer, we can generate a consistent clay slurry material that may be also used in drilling and tunneling excavation practices. So here on the left-hand side, you can see the shear rate dependent viscosity behavior of a bentonite slurry. So you can see that actually the shear thinning characteristics has some scattering, but with a small amount of biopolymer treatment, what we can see a well-controlled shear rate dependent viscosity reduction behavior here. And biopolymer matrix development inside intragranular pore spaces can be observed using an X-ray CT scannings. The continuous complex biopolymer matrix shown in this right-hand side around coarse grains are primarily responsible for the strengthening of coarse soils. So I want you guys to just remember this fact. Actually, these biopolymers, they have some surface charge characteristics. They have, most biopolymers used in my research, they have some anionic, negative charges along the polymer chain. So with this negative charge, they have some, they can easily form ionic bondings with clay surfaces, but with coarse grained soils, which surfaces are electrically neutral. Actually, they don't have direct interaction with the coarse grained particles, but they can just accumulate like this and form a very firm and continuous matrix as a reinforcement member. Using microfluidic chips, we can also measure the production of biopolymer hydrogel matrix among coarse particles. So biopolymer hydrogels are injected to these microchip geometry, which represents sand particles with varying porosity conditions and a diameter of 1 millimeter. We can see how biopolymers condense and form surface coats and interparticular bridges through dehydration using a high-resolution microscopy. And the flock size, number of bones, degree of pore saturation, total bonding length, and other interbonding indicators of biopolymer matrix are investigated. And we are attempting to correlate these indicators with strength parameters such as the interparticle cohesion and friction angle to see, okay, how biopolymers interact and form a matrix among coarse-grained soils, and then how it is revealed to a mesoscale properties of soil particles. When we look at a scanning electron microscopy of biopolymer treated soils, we can clearly recognize the interbonding differences between coarse and fine particles. So on the left-hand side here, we can see biopolymer treated sand. So for coarse-grained soils, biopolymers mainly serve as a surface coverings and intergranular bridges because sand grains have electrically neutral surfaces. However, in the case of clays, as shown here on the right-hand side, biopolymers form direct biopolymer clay matrices with the electrically charged clay surfaces. So the biopolymer hydrogel matrix among coarse particles enhances the shear strength of sands. So when we conducted a direct shear testing on jantan gum biopolymer treated sand, biopolymer hydrogels revealed interparticle cohesiveness for cohesionless coarse particles and increased the friction angle when hydrogel condensed through dehydration. So the point is here. When hydrogels are fully filling the intergranular pore spaces, actually the viscosity of these hydrogels are revealed in terms of what? Apparent cohesion for this soil. And as these hydrogels dry and become condensed, what happens? These condensed hydrogels restrict the movement of soil particles, so they both have an effect on increasing both the dilatancy and the friction angle of the soil. So this is how they enhance the shear strength of sand soils. And this behavior is also realized from triaxial testings. So the hydrogel phase, in fact, has a considerable influence on the biopolymer action on coarse-grained particles. Biopolymers have less of an effect on the friction angle and only provide minimal particle cohesion when they are fully hydrated. But once they go under a dehydration process, what happens? It results in solid interparticle connections, which enhances both interparticle cohesion and friction angle substantially. So, and then let's see what happens to clays. So first of all, when we treat clays with biopolymers, for instance, when we treated a kaolinite clay with jantan gum biopolymer, the direct biopolymer clay matrix formation in clay soils reveals distinctive liquid limit and plasticity index increases, implying the promotion of ionic bonds between clay surfaces and biopolymers. So you can see with a small amount of biopolymer treatment, actually it increases both the liquid limit and plastic limit of clays. And in terms of the enhancement of the electrical statical bonding between clay particles and biopolymers, which reduces the surface potential for ionic bondings, is also implied by the simultaneous electrical sensitivity decrease of clays with biopolymer treatment. So what does this mean? Okay, actually, if a clay has a cation, even it had all clays have a cation exchange capacity. So for instance, the cation exchange capacity of a kaolin clay is around 100. But if it is treated with biopolymers, jantan gum, actually these surface charges can be forms of ionic, especially a hydrogen bonding with these biopolymer monomers. So the overall surface charge density are decreased. So this is how the electrical sensitivity of clays decreases with biopolymer treatment. The electrostatic interaction between clay particles and biopolymers also influences the sedimentation process of clays. So in laboratory, we prepared a very high water content clay suspension, and we simply conducted a sedimentation testing. So with the presence of jantan gum in a highly dispersed clay suspension, jantan gum promotes the early aggregation of clay particles. So you can see here, on the left-hand side here, we have a final sediment of just natural clay, natural kaolinite. And here on the right-hand side, we have clays treated with different levels of biopolymers. And you can see with a high amount of biopolymer treatment, we can see bigger and larger aggregates formed on the bottom compared to this just natural sediment. So what we can see, so jantan gum definitely it promotes the early aggregation of clay particles to form larger aggregates. Because of the jantan gum induced aggregates, the sediment settles faster and also has a higher final density. So what we are expecting, we are expecting maybe if we can ensure some economic feasibility, biopolymer treatment can also be utilized and implemented for reclamination processes. So hopefully we're expecting these small amount of jantan gum biopolymer treatment can have an optimistic function on promoting and accelerating the in situ sedimentation and self-weight consolidation process after we dredge and reclaim a clay to a new site. And the formation of a biopolymer clay matrix improves clay's undrained shear strength, but it does so in diverse ways. When a single water content condition is considered here in the left-hand side, a 0.5% jantan gum treatment produces the largest undrained shear strength, whereas higher biopolymer contents have less effect. As a result, the liquidity index and undrained shear strength have a single relationship, indicating that biopolymers have no effect on the clay mineralogy and are exclusively used to produce interparticle connections and pore fluid thickening. So when we change our perspective to a constant void ratio scenario, however, more jantan gum concentrations leads to increase the undrained shear strength. Triaxial test experiments with undrained conditions reveal a progressive increase in undrained shear strength, also indicating that jantan gum content greater than 0.5% primarily increases the pore fluid viscosity. As a result, jantan gum treatment has the ability to improve the ground bearing capacity of weak and soft clays, allowing for in situ activities to be implemented. The compressibility and swelling of saturated clays are both increased by jantan gum treatment, although the effect on swelling is more noticeable. In fact, biopolymer treatment decreases the coefficient of consolidation due to the pore clogging effect induced by biopolymer hydrogels. However, this means that biopolymer clay mixtures have a potential to be used as what? Ground hydraulic barriers for groundwater control. So we are conducting some preliminary research to assess the feasibility of using biopolymer treated clay as a clay liners for municipal waste deposits nowadays. In fact, because the pore clogging effect caused by biopolymer hydrogel, biopolymer treatment reduce, and in terms of the shear strength parameters, these Jantan-gum clay matrix has a very promising function on increasing both cohesion and friction angle. So you guys I want you to remember the biopolymer clay matrix becomes a very important key for the entire soil strengthening of these biopolymer treatment. To sum up, the soil strengthening process caused by biopolymer-based soil treatment can be summarized as what? Well, in the case of coarse-grained soils, these biopolymers, these hydrogels just form a continuous matrix among granular particles. So they have a slight improvement in the cohesion, while they have less variation in terms of friction angle. But with the presence of clay, the direct biopolymer clay matrix formation, which has an immediate impact on the soil cohesion and friction angle. The well-formed biopolymer clay matrices surrounds coarse grains and hardens by dehydration in the presence of coarse particles, revealing an aggregation effect, which we defined it as a conglomeration effect, revealing, that optimized both interparticle cohesion and friction angles. Meanwhile, when we examine the shear moduli and damping properties of biopolymer treated sands, we found that despite the fact BPST reduces the G over Gmax curve earlier than untreated sand, the absolute Gmax value is significantly higher, and BPST also offers a significant increase of the damping ratio. So as a result, we are finding whether these biopolymer treatment could be functionable for a seismic proposals. So nowadays, what we are doing in laboratory, we're conducting cyclic simple shear assessments on loose sands with and without biopolymer treatment. And what it shows? It shows that biopolymer treatment shows a significant improvement on the cyclic stress ratio for same number of cycles. So as a result, for instance, with the cyclic stress ratio, actually biopolymer treatment increases what? Almost 4 times compared to what? Untreated soil, untreated sand conditions. So we are doing more study to see if biopolymer treatment can be used to mitigate seismic energy and also reduce the liquefaction potential for high liquefiable sand deposits. Okay, so when we take a look on the hydraulic behavior, so biopolymers, they actually increase the water retention capacity of soils because these biopolymer itself are very hydrophilic. So it means they hold water longer than untreated condition. And when we take a look on the wetting behavior, actually the wetting behavior is quite distinctive. When Jantan-gum is treated, Jantan-gum causes particle agglomeration and acts as a subsequent water transfer when the Jantan-gum level is less than 0.5%. But when the Jantan-gum content exceeds 0.5%, swelled Jantan-gum hydrogels clog the pores and interrupts the water transfer. So we have to be very careful when we want to control the soil hydraulic conductivity when for these biopolymer treated conditions. So the hydraulic conductivity of biopolymer treated soil significantly reduces as a result of pore clogging caused by these biopolymer hydrogels. So as a result, biopolymers have the potential to be used for several groundwater control practices. So the pore clogging effect generated by BPST gradually declines as the hydraulic pressure increases. So nowadays we are also attempting to find which water pressure condition will be the critical condition for these biopolymer treatments. So we are also aiming and we are also processing to enhance the gel strength to make it more stronger and to be more resistible. Okay, so durability is always a key consideration when it comes to soil engineering. The mechanical endurance of biopolymer treated sands was assessed using cyclic wetting and drying and freezing and thawing programs in our laboratory. So with repeated wetting and drying, Geotechnical treated sand specimens become more ductile, resulting in a steady drop in UCS and elastic moduluses. The strength and stiffness of Geotechnical treated sands, on the other hand, are less affected by repeated freezing and thawing. But when we take a look on gel type, gel uncomb-treated sand, both cyclic wetting and drying and freezing and thawing results show a promising durability, even compared to what ordinary 10% treated conditions. So we are expecting, well, yeah, we admit, yes, these biopolymer treatments, they are not a permanent countermeasure, because these carbohydrates, they have some biodegradation and also some decay due to cyclic wetting and drying and cyclic freezing and thawing programs. But what we are expecting is, at least for a short to medium term time period, they will be effective. They will provide significant strengthening, ground hydraulic water conductivity control. So actually we are mostly focusing to use these biopolymers for temporary ground support or improvement practices. So let me show you some more detailed examples. So, well, indeed, yeah, if the soil has some clays, the durability becomes better. Yeah, it's more durable. Okay, so the first thing we are conducting is to use biopolymers as a new grouting material for ground injection and hydraulic conductivity control practices. So we're using these biopolymers. So due to the shear thinning properties, we can control the injection rate with different flow rates. So in laboratory, we're using this sand column and we're injecting biopolymer hydrogels and see what happens to the permeability and other considerations. So definitely what happens here? If we have a higher yield stress, it means that the injectability is interrupted. So if we want to use biopolymers as a new grouting material, we have to consider the yield stress. If we apply a higher pressure, definitely, okay, the injectability becomes better. And if the soil has a higher permeability, which means if the soil has a higher porosity, of course, yeah, the injectability becomes also better. So, well, compared to an untreated condition, well, if we inject biopolymers into these sands, of course, they have a significant impact on decreasing and reducing the ground hydraulic conductivity. However, there remains a concern about the washout of these biopolymer grouts. So on the right-hand side here, what we can see is, if we increase the inlet water pressure up to after some certain points, what happens? The hydraulic conductivity increases again. So it means that what? These biopolymers are starting to be, washed out from the pore spaces if we have some extreme hydraulic water condition, pressure conditions. So how can we implement these biopolymers in field? So our first interest was using these biopolymers to control or even mitigate soil erosion. So more extreme downpours and floods are being caused by the present global climate change, as I already explained in the introduction. As a result, we must devise a practical countermeasure to improve the mechanical stability of earth dams or levee structures in the face of a variety of hydraulic erosion triggers. So in laboratory, we brought in situ levee soil and treated it with different biopolymer conditions. We attempted different types of biopolymer blends using xanthan starch, casein, and cross-linked starch, and also malonic acid. We used an erosion function apparatus EFA with a P-wave monitoring system, and we assessed the erosion behavior of different soil compounds. So you can see here on the bottom side, so compared to pure sand, biopolymer treatment definitely increases the critical shear stress, which is the point where soil starts to be eroded, and also it reduces the erodibility coefficient significantly. So biopolymer both enhances the starting point of the erosion in terms of external shear stress, and also even though erosion is initiated, actually biopolymer treatment restricts and provides more resistance against erosion. So we have performed different types also. So compared to a non-treated reference, actually pure sand, the critical shear stress is just around 0.07 pascals. But with biopolymer treatment, depending on different types, but they all have an effect on increasing the critical shear stress. And the untreated pure sand has a erodibility coefficient around 3,900, but biopolymer treatment significantly reduces the erodibility coefficient. So biopolymers has a very optimistic function on enhancing the soil resistance against erosion. So with the laboratory findings, we have performed the numerical prediction using a Syracuse EFA program suggested by the Texas A&M, and we can see these biopolymer treatment has a very promising effect on reducing natural scour in river structures. And also in laboratory, we are conducting open channel erosion testings to simulate severe overtopping and internal piping conditions on biopolymer treated levee models. So on this slide, on the top, you can see a levee model from the bird view with untreated condition here and biopolymer treated condition on the bottom. So with different observations, you can see the control condition, biopolymer with no biopolymer treatment, actually once the overtopping has initiated, actually the entire levee was just eroded just after 15 minutes. But for biopolymer treated levee model, even 330 minutes has been passed since the point of overtopping initiation, the structure is still remaining at its own location. So how does it, what is the expect? So this is the statistical comparisons. So, well, we performed more larger scale studies in field. So what we have, conducted a large scale model testing using this levee model with and without biopolymer treatment. You can see since the overtopping has been initiated, actually just only 2 minutes were required to entirely erode an untreated levee model. But if the surface is slightly treated with biopolymers, yes, it can delay the failure up to 12 times, later compared to untreated condition. And a large scale levee model has been fabricated and treated with different surface conditions. So we also simulated an overflow from the overtopping on this levee model. So you can see, compared to a control condition, biopolymer treatment on a surface can delay the entire erosion and collapse. And just last year, just 3 months ago, we also conducted a large-scale overtopping simulation on a levee model. So we constructed this earthen levee model. So we have also simulated this overtopping. So we can see, first of all, it was very interesting. The surface vegetation density has been significantly improved when we treated the surface with biopolymers, and also it showed a very promising resistance against overtopping. And then what will happen to an internal erosion count measure? So we fabricated a levee model with a concrete structure embedded on the bottom. So this concrete represents a channel embedded under a levee structure. So we have initiated some erosion from the bottom of this embedded structure, and see what happens to the internal erosion. So here's a video here. So on the left-hand side, it is a non-treated model, and on the right-hand side, this is a biopolymer-treated model. So you can see the levee model without biopolymer treatment. Yeah, it shows progressive internal erosion, and it just suddenly collapses with time, while this biopolymer-treated levee model, it shows a higher and promising resistance against internal piping erosion. Yeah, so with the same timeline, you can see, okay, when the untreated levee is totally collapsed, still biopolymer levee is working well. And we also conducted a large-scale in situ testing, so we can see biopolymer treatment around a structure can reduce 77% of the internal erosion along the interface. Okay, there's another interest from our side to apply biopolymers. So we are aiming to apply biopolymers for anti-desertification practices. Because why? First of all, biopolymer treatment has an impact on increasing the soil erosion resistance. And what we found is these biopolymers also have a promising and optimistic function on promoting, accelerating, facilitating the vegetation growth in terms of seed germination and crop growth. So we are combining these together. And also under a severe drought condition, biopolymer treated soils, the crops in biopolymer treated soils shows a higher survivability. So with these concepts, nowadays we're also finding to apply these biopolymers for anti-desertification practices. Okay, So let me just move on. So what other practical implementations can be possible? So 10 years ago, we just preliminary attempted slope stabilization with biopolymer hydrogels. We also successfully construct a non-cement, non-asphalt pavement with just biopolymers and in-situ soil mixtures. We also constructed an adobe building with biopolymers and soil itself. And for some more advancements, we invented and we developed a biopolymer spraying system using in-situ soils and biopolymer hydrogels simultaneously. So you can see here that we can spray biopolymers and soil together to form a uniform surface protecting layer. And what is also expected? Well, actually, what we have to ensure is will the field behavior be similar or repeatable compared to the laboratory condition? So we collected around 300 samples from the field. We performed some statistical analysis, and we found that, okay, well, the field and laboratory strengths are quite similar to each other. So these biopolymer treatment is quite repeatable and reliable for field implementations. Yes, okay. And this is also scene one. So what other future applications can be possible? We can see ground improvement, post-wildfire site recovery, non-asphalt pavement, earth buildings, and afforestation practices. And the economic feasibility is also main consideration. Well, to give you a conclusion, it is nowadays very, very competitive and, well, economic. Okay, so to close my talk today, well, when we consider general ground improvement practices, we have to consider soil type, what is the proposed, what material or what binder is going to be used, what equipment is going to be implemented, and what will be the environmental impact from this practice. So for biopolymers, actually, they all satisfy and has a promising fact for these 5 different considerations. So, well, to give you a closing remarks, microscale interaction between soil grains and biopolymers improves microscale mechanical properties of soils. Biopolymers can be a cementless, eco-friendly ground improvement technique applicable for various civil and geotechnical engineering fields, including levee constructions and anti-desertification practices. So, yeah, this is the end of my presentation. So before I sign off, I'd like to express my gratitude to my wonderful team who have all devoted themselves to this research for the past 10 years, and also definitely will continue to do so. So, well, thank you. And this is the end of my presentation. Oh, well, yes. So actually, when you look at the molecular structure of biopolymers, actually, the hydroxyl group, the OH group, are mainly composed along the surface. So this provides an ionic characteristic. So definitely, these biopolymers, when they bind, when they form ionic bonds with the clay particles, they mostly prefer to bond on the edges, not the faces. Because if we look at the clay particle, the faces are mostly negatively charged and the edges are positively charged. So when we look at the SEM images or TEM images, we can recognize they mostly interact with the edges. However, with the presence of some cations, these biopolymers, they can accumulate much better and form some more strong and stiff hydrogels. So that is the main purpose. That is the main starting point nowadays. So nowadays we are trying to enhance the strength and also as well as the durability of these biopolymer treatments. So with the presence of some special cations, we found that we can definitely increase the durability, the strength, the stiffness, the viscosities of these biopolymer hydrogels. So, well, most biopolymers, they are negative. Yes, they can, if we add some salts or sodium or potassium, yeah, these biopolymers, they directly form electrical ionic bonds with those cations. Oh yeah, so well, actually these, well, I understand this point. So actually, if we just add a small wall of biopolymer treatment to an existing building, actually it will not be so functionable. So, but when we newly construct or if we repair something with these biopolymer treated soil. So the basic idea was like this. 10 years ago, I remember there was a very severe earthquake in Iran where there was a devastating collapse and failures of those earthen and soil buildings. So, well, our suggestion is, well, when we construct an earthen structure with these biopolymers, definitely they will show a higher damping ratio and resistance to shaking modes. So, well, for existing structures, I'm not sure, but well, for ground improvement practices, if we have a soil deposit which has a high liquefaction potential, then our aim is to, well, inject some biopolymers or directly mix them into the ground to just, well, enhance and improve the liquefaction safety against liquefaction. And so, well, nowadays we're conducting just simple cyclic simple shear and cyclic traction testings. But if we come out with some more promising results, then our next step will be definitely just, well, maybe conducting some shaking table testings on some models and model grounds and model structures above it. Yeah. So I already showed you some cyclic wetting and drying behaviors. So yeah, for pure biopolymers, they do. With the presence of clay, so actually the pure pure biopolymer hydrogel, they do have some degradation. Yeah, but if we have a clay, so when they are strongly bonded with clay particles, actually it enhances and promotes the making more durable. And with some more cation treatment, we are expecting that it will have another positive effect on improving the durability of these biopolymer hydrogels. So, well, yeah, let me work more hard to see what comes up. Yeah.